Today is chapter 2 of organic chemistry. This will be a bit longer than chapter 1, as chapter 1 was mostly review. So you don't have to go through this in one setting. So we'll start off with wave properties of electrons. Standing waves vibrates in fixed location. A wave function, or size, mathematical description of size, shape, and orientation. Amplitudes may be positive or negative, and a node is when the amplitude is 0. So here's an example of, for example, p orbitals in which you have a positive node and a negative positive amplitude and a negative amplitude and going through a node at the nucleus, and this can be represented as, this is a p orbital with a negative and a positive with a nodal plane. Linear combinations of atomic orbitals. These are combining orbitals between two different atoms. When you do so, this combination is bond formation. Combining orbitals on the same atom is known as hybridization, and there's usually conservation of orbitals. Waves that are in phase add together, amplitudes increases, waves that are out of phase cancel out. So in last chapter we talked about s orbitals and p orbitals. Now we'll be talking about combining some of these orbitals linearly, and that's why it's a linear combination of atomic orbitals. Sigma bonding is when the electron density lies between the nuclei. A bond may be formed by two s orbitals, ss, or two pi orbitals, or p orbitals, pp, or s and p, or a hybridized orbital overlaps. The bonding molecular orbital, or MO, is the lower in energy than the original atomic orbitals, and the antibonding, that's a star orbital, is higher in energy than the atomic orbital. So pictorially, here's a sigma bonding molecular orbital. So if we take one s, right, and then in the case of s orbitals, there's the node, the plane in the center, you have most electron density. As a result, you don't have the node as in the case of the p orbitals, as we had shown before. And so you have another s orbital, so they're going to be overlapping. And when they overlap, it's represented by two positives. And when you're adding them together, that overlap area exhibits some sense of positive, and so that it goes through with a positive kind of overlap called this is your bonding molecular orbital. And so this would be a sigma bonding between two s. So formation of a sigma bond molecular orbital is when one s orbitals of two hydrogen atoms overlap in phase with each other. They interact constructively, forming a sigma bonding molecular orbital. Here's sigma star antibonding molecular orbital. In sigma star antibonding, you have positive and a negative. And then when you put them together, you don't have an overlap, as instead you have a repulsion. As a result, you form a node, and this is called sigma star antibonding. So this is when two 1s orbitals overlaps out of phase. They interact destructively to form an antibonding molecular orbital. So if we look at the H2 atom and look at the energy profile, here's 1s. And here's the other s. When it's doing normal molecular bonding, molecular orbital, so the bonding molecular orbital, you're going to see overlap. And this is your sigma bonding molecular orbital. By contrast, your sigma star, your antibonding molecular orbital, will have a node across it. And so when the electrons fill, they're going to stay in the sigma, not the sigma star. In the case of chlorine, diatomic chlorine, the PP overlap, it's similar to that of the S. In this case, you have your positive nodes aligning up with one another, forming kind of an overlap. So when the two p orbital overlaps along the line between the two nuclei, a bonding orbital and an anti-bonding orbital will result. This is the bonding orbital, and this will be lower in energy. Most of that electron density is centered along the line between the nuclei. This linear overlap is another type of sigma bonding molecular orbitals. So if we have a problem, draw the sigma star antibonding orbital that results from destructive overlap of two px orbitals. Please, what does it look like? So that's when you have now the positive and the negative not aligning with one another and then forming a node where you have a sigma star antibonding molecular orbital. This is going to be higher in energy. You can also have S and P orbital overlap, in which you have a px and an s overlapping one another, in which now you have this sigma bond overlap where they're constructively working together. You can have a px and a negative x, so this is oppositely charged. This will generate a node. This is now your sigma star antibonding molecular orbital, which is higher in energy. Now, if we look at pi bonding is when we're looking at not the bonding that's happening directly on, rather it's kind of a sideway overlap. So shown below is the constructive bonding when you have the two p orbitals aligning with one another. This sideway overlap allows constructive overlap, allowing for sigma, or not sigma, but pi bonding occurring. You can have a pi anti-star bonding occurring in which they're oppositely charged, which a node is developed, and this is higher in energy. It's akin to the sigma star antibonding molecular orbitals. So if we look at multiple bonds, a double bond, where you have two pairs of shared electrons, they consist of a sigma bond and a pi bond, essentially. And a triple bond, which has three pairs of shared electrons, consists of a sigma bond and two pi bonds. So here is a double bond in which you have a sigma bond, and then the p's have a pi bond on each side. So molecular bonding and orbitals are important because it dictates molecular shapes. So if we look at methane, for example, carbon, hydrogen, so it's in a tetrahedral arrangement in which you have angles of 109.5 across the way. But when you have, for example, ethylene, they're now, with the double bond, the bond angles of the carbon, hydrogen are different. You have 120-ish in the case of the carbon, hydrogen, and then for the carbon, hydrogen, you have 116 going across. And then if you have a triple bond, in terms of acetylene, they're about 180 degrees. So bond angles can't be explained with simple s and p orbitals. Valence shell electron pair repulsion theory, or VSEPR, is used to explain the molecular shapes of the molecules. Hybridized orbitals are lower in energy because electron pairs are farthest apart, and hybridized orbitals is what allows us to understand the molecular shapes. So let's look at sp hybrid orbital. Hybrid orbitals results when an orbital of the same atom combine. Two orbitals, s and p, combine to form two sp orbitals. Linear electron pair geometry is established with sp, and it has a 180 bond angle. So here is sp, where your s is overlapping with a p, and in this case you have an sp orbital. When you have that overlap, the positive kind of constructively organize itself so that it becomes a bigger lobe on one side with a smaller lobe on the other side. Same thing here. All the positive ones will have a bigger lobe on one side and a smaller orbital on the other side. Important to note is that the number of hybrid orbitals formed is always the same as the total number of s and p orbitals hybridized. So if we look at the bonding of beryllium hydride, as shown here, you have a beryllium, which is an sp, right? That is then being overlapped with just an s orbital from the hydrogen. And the other beryllium, sp, overlapping with another hydrogen. This then gives you a superimposed picture with 180 degrees, consistent with acetylene as shown before. And the bond angle of beryllium hydride is 180, and geometry is linear. Now if we look at sp2 hybrid orbitals, you're going to take s and px and py, right? There's two p orbitals then hybridizing with the s. When that happens, you're going to generate constructive formation where you have one lobe, positive lobe being fatter than the negative lobe, and you're going to have it in one direction, another direction, and another direction shown here. These are going to be the sp2 hybrids. Remember, you're taking three things and combining it, so you're going to generate three things in the end, and these are the three things that you're going to generate in the end. These three orbitals form 3sp3. They're going to be trigonal planar in geometry, and their bond angle is going to be 120. And so here is what it looks like. And then the PZ is missing. That PZ just remains as a PZ unhybridized orbital shown here. So let's look at a problem. Borane BH3 is not stable under normal conditions, but has been detected at low pressure. A. Draw the Lewis structure for borane. B. Draw a diagram of the bonding in this molecule and label the hybridization of each orbital. And C. Predict the HBH bond angle. So you should be able to do this really quickly. This is the Lewis dot structure of boron. Now, boron is hybridizing s and p orbitals, so you're going to have an sp2 orbital. So you're going to have three of them shown here, and so you should be drawing them out as lobes, as shown here. And then you're going to have an overlap with a sigma from the hydrogen with the sp2 for each hydrogen being bonded to the boron. As a result, because it's an sp2 hybrid, you're going to have the bond angles be 120 degrees all the way across. In terms of sp3, sp3 is a hybridization of s with all the three p orbitals, x, y, and z. This then forms four sp3 hybrids like this in a tetrahedral shape in which the bond angle is about 109.5. If we look at the summary of all the hybridization and geometries, 2, 3, and 4. 2 is when you take S plus P to get a SP. This will generate a linear geometry with 180. These should be memorized. 3 will be 1S and 2 P's, give you SP2. This will be trigonal, 120. 4 is 1S and 3 P's, generating SP3 will generate tetrahedral, 109.5. So here's a problem, another problem that you should be doing. Predict the hybridization of the nitrogen atom in ammonia, NH3. Draw a picture of the three-dimensional structure of ammonia and predict the bond angles. The hybridization depends on the number of sigma bonds plus the lone pairs, and so you generate your Lewis dot structures. Either one is fine when you have a lone pair. So when you're drawing this as an sp3, because there's sp3, you're going to generate the tetrahedral in which one of the sp3 orbital has the lone pairs in it. And because it has a lone pairs, you're going to get electrostatic repulsion on this side, leading it to be slightly smaller than 109.5. In this case, it's 107.3. So when you have sp3s interacting with one another as a sigma bond, right? So you have two carbons, two methyl groups to form an ethyl group. These will form a sigma bond across, and this can rotate across that single bond. So you can be eclipsed or staggered. So ethane is composed of two methyl groups bonded by this sp3, overlap of sp3 hybrid orbitals, and that there is free rotation along the single bond. In the case of ethylene, in which you have a double bond, ethylene has three sigma bonds formed by its sp2 hybrid orbitals, shown here, in a trigonal planar geometry, right? This is absolutely correct. And then there's an unhybridized p orbital on top and bottom of this, shown here, in which you have pi bond overlap. And this is also occurring so that you have sigma and then pi bond overlap, generating the double bond. If we wanted to rotate this double bond, it's not rotatable. In order to rotate this, we'd have to break the pi orbital or pi bonding, and that would be too costly an energy in order to do that. And so you can't go from one to the other state. So double bonds cannot rotate, Compounds that differ in how their substituents are arranged around the double bond can be isolated and separated. So this you have them cis, meaning on the same side. These you have this methyl groups on the trans on different sides. These two are different arrangements and thus can be separated. Whereas if you have a methyl where you have a single bond, you cannot separate those because you have them freely rotatable. This leads us to the definition of isomerism. Molecules that have the same molecular formula but differ in the arrangement of their atoms are called isomers. Constitutional or structural isomers differ in their bonding sequence. Stereoisomers differ only in the arrangement of the atoms in space. So for example, here are constitutional isomers. Here's pentane, isopentane, and neopentane. Constitutional isomers have the same chemical formula, but the atoms are connected in different orders. Constitutional isomers have different properties. The number of isomers increases rapidly as the number of carbon atoms increases. So as you go higher, this is five-membered molecule, to higher numbers 6, 7, 8, you can make much more constitutional isomers because you can connect them very differently. Geometric isomers fall under cis and trans. These are stereoisomers, or stereoisomers. Stereoisomers are compounds with atoms bonded in the same order, but their atoms have different orientations in space. Cis and trans are examples of geometric stereoisomers. They occur when there is a double bond in the compound. Since there is no free rotation along the carbon-carbon double bond, the groups of these carbon can point to different places. So again, here's a cis-butene and trans-butenes. These are known as stereoisomers because they're different. And these are constitutional isomers because their connectivity are absolutely different, right, from one another. Identical groups on one of the double bonded carbons implies no cis-trans isomerisms. This is a good hint. So for example, if these are identical and they're on one side, there's no cis-trans isomerism for this. Again, these have three of the same ones of which 2 are on the same side. Again, this doesn't exhibit cis-trans isomerism. Bond dipole moments. So we talked about dipole moments in the last chapter. Here we're going looking at bond dipole moments. So as you can see, this is ethane, in which they're all identical. There's no dipole moment. This is nonpolar. But then as you go from and add on different groups to the CH3, you can change the polarity and show dipole moments in which it's going to the more electronegative atom. In the case it's nitrogen, oxygen, and chlorine. And as you increase in polarity, it's going here. And then you can if you completely increase polarity, you can get to ionic bonds. Dipole moments are due to differences in electronegativity, as we've seen in the previous chapter. They depend on the amount of charge and distance of separation, and they're measured in dBi. So if we look at molecular dipole moment, we looked at each atom. We can see, for example, this is a whole dipole moment of the whole molecule, but each of the atoms that are arranged around the central carbon has a dipole moment. So the CH has a dipole moment and going from H to C to the negative, and then the C to the chlorine is as a dipole moment going that way. So the overall dipole moment of this molecule goes from the left to the right. Same thing for the rest. In this case, you have chloroform, in which now you have one hydrogen and all of them are chlorine. Here you have all of them going out from the carbon. This gives you a net zero dipole because all of them are being pulled out from the carbon equally. And then here, if we look at this 1,2-dibromoethane, we see positive from the hydrogen to carbon, and then positive from carbon to bromine. So the overall dipole moment is from left to right. So the molecular dipole moment is a vector of the sum of the bond dipole moments. It depends on the bond polarity and the bond angles. Lone pairs of electrons contribute also to the dipole moment. So if we look at lone pairs and dipole moments, here are examples where you see now lone pairs contributing. So again, here's ammonia, in which electrons from the positive side from the hydrogen to the nitrogen, and then nitrogen to the negative, right? So this is negative electrons. Overall dipole moments left to right. Same with water. Overall dipole moments left to right. Here, acetone, dipole moment here, and then to the electrons. And then here's acetonitrile, dipole moment from the carbon to the nitrogen, and then nitrogen to the electrons. In terms of intermolecular forces, these are the strength of attractions between molecules influencing what is the melting point, boiling point, and solubility of compounds. There are different classifications of attractive forces. They fall under these categories: dipole-dipole forces, London dispersion forces, hydrogen bonding in molecules with hydroxide or NH groups. If we look at dipole-dipole forces, dipole-dipole interactions result from the approach of two polar molecules. If their positive and negative ends approach, the interaction is an attractive one. If two negative ends or two positive ends approach, the interaction is known to be repulsive. In a liquid or solid, the molecules are mostly oriented with the positive and negative ends together, and the net force is attractive. Here are some dipole-dipole interactions shown here, and here, and they can be symbolized by here, showing interactions, and here's our repulsions. So I'm going to stop here and then continue on with the next part.